All right, so quick review of Newton's second law, okay? Newton's second law deals with any situation where there is an unbalanced or net force. If there is a net force, then the object is going to undergo what kind of motion? Accelerated motion, right. It's going to accelerate in the same direction as the net force. Okay? Newton's first law deals with situations where there's no net force, and thus the object either remains at rest or travels at a constant velocity. So we've gone over a number of fairly simple Newton's second law problems that involve, here's the net force, what's the acceleration, things like that. Okay? Now we're going to start getting into collinear kind of vector Newton's second law questions. Okay? So elevator problems are perfect examples of collinear vectors producing an acceleration. So I've got this person in an elevator. The combined mass of the person and the elevator is 600 kilograms. So I need to draw a free body diagram better than this one, even though it's a pretty picture. It doesn't have the mass in it, and we said that that's a key ingredient in any free body diagram. So I'm going to replace that great diagram of the gentleman in the suit in the elevator with a box with the 600 kilograms drawn in the middle. All right? There are two forces acting on the elevator. Gravity, which pulls it down, and the tension in the elevator cables that are used to lift it. Okay? That's how an elevator works. Okay? If you want to raise the elevator, you lift it using the cable. If you want to lower the elevator, you lift it using the cable. You just don't pull as hard. Okay? Think about if you've ever, lowered something with a rope. You're still pulling up on the rope, even when you lower it. You're just not pulling on the rope as hard as gravity is pulling until the object descends. If you want to raise it, you have to pull harder. That sort of makes sense? Okay. So what they tell us in this question is that the force in the cable, which is a tension, okay, is upwards. And it's 6,500 newtons. Okay, and what was the other force we said was present? Gravity. Okay, and gravity is acting down. How do I calculate gravity? I think this is where we left off on Wednesday. We didn't get much further than this. Okay. We calculate the force of gravity very similar to the way we calculate net force. Okay? F net is mass times acceleration. Well, any force is mass times acceleration. It's just the acceleration that force would produce. So for the force of gravity, that acceleration is the acceleration due to gravity, okay, which is obviously on your formula sheet. Okay. So I know the mass of the elevator, and I know the acceleration due to gravity. So all I would have to do is go 600 kilograms times 9.81 meters per second squared, and I would have the force of gravity, or the weight of the elevator. And that's going to be 5,886 newtons. Okay, so anytime you need to calculate the force of gravity, that's how you do it. You take the mass of the object and you multiply by 9.81. Okay. Now that I know the force upwards on the elevator and the force downwards on the elevator, which direction is this elevator going? Up. Because the force up is, it's bigger, yeah. Okay? There's the net force, right? The vector sum of 6,500 and 5,886 is 614 newtons up. Okay? So this elevator is going to move up. In fact, it's going to accelerate up. Okay? So the next step here would be, okay, and this is something we have to remember, F net is not just mass times acceleration, it is also the vector sum of all forces. In this question, the two forces are the forces in the cable and the force of gravity. Okay, so when I calculate the net force in this question, okay, that's going to be 6,500 newtons plus negative 5,886 newtons. It does, after all, say the vector sum. Obviously, most of the time you would just subtract those numbers because that makes more sense. Okay, so when we do that, we're going to get 614 newtons up. Okay, what does the question want? What's the acceleration? Can I find that now? Okay, if you recall, I said in every Newton's second law question you do, you're probably going to have to do both of those. Well, I already did the vector sum of all forces part, so if I want to find the acceleration, I'll have to do the m times a part now. So a will equal F net divided by m. I'll take that 614 newtons up and divide it by the mass. 600 kilograms. Okay, now recalling that a newton is a kilogram meter per second squared, if I divide a kilogram meter per second squared by kilograms, I'm going to be left with meters per second squared. Okay, I think it comes out like 1.02 or something like that. Okay, so there's the acceleration of the elevator. Did I have to do any like crazy math? I had to subtract two numbers and divide two numbers. Oh, and I had to multiply 600 times 9.81. Okay, here's the pattern you're going to see throughout this unit. There isn't any crazy math. That's all you'll ever have to do. Maybe a little bit of vector components. That would be the most complex math you'd have to do. A little bit of vector components and adding, subtracting, multiplying, dividing. That's all it ever comes down to. Here's where it gets complex. The vector sum of all forces part can sometimes be pretty challenging. Not mathematically, but just to determine A, what are the forces that are involved? B, what direction are they going? What effect are they going to have on this system? Okay, blah, blah, blah. You're going to have these things to figure out. It's the context that's challenging, not the math. Okay, the math in this unit is pretty straightforward. Okay? That's why when people say, I can't do physics, I'm not good at math, I'm like, neither am I, and I teach it. So you don't have to be all that good at math to do physics. What you have to be able to do is have an understanding of how the physical world works. Okay? Visualize in your mind, using your life experience. How does an elevator work? Oh, okay, and think about it, right? I mean, think about this. When you get in an elevator and you press the, the third floor button and you start to move upwards, how do you feel? Heavier or lighter? Heavier, yeah. You're going to get pushed on by the floor. Okay, the floor of the elevator has to push you upward. It has to lift you. That means it has to push with a force greater than your weight in order to lift you up. So you'll feel a little bit heavier. Similarly, if you get in the elevator on the third floor and press the ground floor button, it feels like your feet fall out from underneath you for a second. Okay, while the elevator releases the brake on the cable and lets you fall before catching you, because you don't fall all the way down, okay, but catching you and then letting you travel downward slowly. Okay, everyone follow me there? Okay, so that's all that an elevator does. Are there lots of different examples of elevators that aren't elevators? If I throw something up in the air, am I dealing with an elevator situation? I am. I have the force of my hand pushing up on the object I'm throwing, and the force of gravity pulling down on the object I want to throw. That's still an elevator question. Okay? What about a bungee jumper? Is that an elevator? After the bungee cord has started to get tension in it, it's an elevator. Gravity is pulling down, the bungee cord is pulling up. Okay? It's an elevator. Anything moving straight up and down is an elevator. Okay? What force do people forget in an elevator question if I don't tell them about it? Gravity. You'd be surprised. If I give you a question about throwing a rock in the air, how many people will forget gravity is involved? Okay? If I say you throw a rock up in the air with 200 newtons worth of force, people write F net equals 200 newtons. They'll just like, oh, suddenly gravity doesn't exist. There's no up if there's no gravity. Gravity tells you which way is up and down, right? Does that sort of make sense? So elevator questions are anything that's moving vertically up and down. All right, questions on that elevator question? All right, same elevator, right? So the mass is still 600 kilograms, okay? And you also then know the force of gravity because you already calculated it, 5,886 newtons, okay? I want you to calculate the acceleration of the person in that situation. Okay, so what's different about this situation? Which way does the elevator go here? It goes down, right? It goes down because the force up is now less than the force down, right? We're told in this one that the upward force, or the tension in the cable, is only 5,200 newtons. Okay, still a 600 kilogram elevator, okay? And then that means that this force is still the force of gravity of 5,886 newtons. Right, so now, can I still calculate F net? Same way I did the last time. Same way I do in basically every one we're going to do. 5,886 newtons minus 5,200 newtons, okay, is going to give me 686 newtons down. All right, so I know the net force is down. That means that the elevator is going to move down. It's not just going to move, it's going to accelerate. Right, so I should then be able to calculate its acceleration by going F net divided by mass, 686, divided by 600, and that should give me 1.14 meters per second squared down. Okay, everybody all right with that? Okay, you don't have to do number 2. Okay, I would like you guys to write down and try question number 1. Bungee jumper, okay, still an elevator, even though it's a bungee jumper, right? See if you can apply what we learned in the last 2 to solving that one. Okay, what's the first thing I should do for this question? Or for any question for that matter?
Draw a diagram.
Draw a diagram, exactly. Okay, draw a free body diagram in this case. Okay, we know the mass of the bungee jumper is 55 kilograms. Okay, and we know that the bungee cord is already being stretched, okay, and is exerting a force of 825 newtons up. That's good. You want the bungee cord to do that, otherwise it's just falling, not jumping. Okay. Now, what's this force? Gravity, yeah. Is it bigger or smaller than the 825? Smaller. She's slowing down. That's what the bungee cord's supposed to do. So I've already made a mistake with my drawing here. That arrow should be shorter. So that's going to be force of gravity, and it's going to be m times g. So 55 times 9.81. So 539.55. Okay, so now I have the 2 forces. They want the acceleration. What can I calculate right now? I can calculate net force, okay? And I'm going to calculate net force by doing the sum of all forces. 825 newtons up minus 539.55 newtons down. Okay, so I'm going to do that. Okay, so 825 minus that force there. All right, 285.45 newtons up is my net force. So which way is she accelerating? Up. Which way is she going? Down. Yeah, that's okay. When you bungee jump, you're still going to be moving downwards even after the bungee cord takes up. You're just going to stretch the bungee cord and go slower and slower and slower. Okay, so I can now calculate then her acceleration, which is what the question wanted in the first place. F net divided by m. So We did sum of all forces. Now we're doing m times a. We're just manipulating it for a. That's going to be 285.45 divided by 55 kilograms. Okay, so her acceleration upwards is 5.2, because we only have 2 significant digits there. 5.2 meters per second squared up. Okay. Everybody all right with that? It's just an elevator question, right? But it's a bungee jumper. But it's an elevator. Okay, it's still a context thing. Right? Now, for question number 2, we don't have to do anything for this except talk about it. Okay? During the bungee jump, the velocity of the 55 kilogram woman at her lowest point is 0. Not because she smashes into the ground, okay, but because the bungee cord worked. So the bungee cord takes up and she stretches the bungee cord, slows down, slows down, slows down, for an instant stops at the maximum amount of stretch, where, by the way, the cord is pulling the hardest, okay, and her acceleration would then be the greatest. Okay? For any elastic object, the harder you pull, the more it pulls back. And the more it pulls, the greater the acceleration it can produce. Everyone okay with that? So when it is stretched the most, she is going to experience the most acceleration, even though at that instant, she's not moving. That's where she stops before moving back up. Because when you bungee jump, okay, you stretch the cord, and then it shoots you back up in the air, and then you come back down, and shoots you back up in the air, and then eventually you just kind of oscillate until somebody lowers you down. All right? Everyone okay with that? So that's what question number 2 is asking about. Compare the direction of her acceleration at the lowest point of the jump, up, to when she jumps off the bridge, down. Okay? They're in opposite directions. Okay. Okay, I want you to draw this example. Okay? I'll kind of vocalize it here once you're done drawing it out and writing down that one other piece of information. Then I'm going to tell you what I want you to calculate. Okay, so here's the situation. There's a 20 kilogram mass being pulled up this ramp. Okay? The force acting down the ramp, right, which is not gravity, but it's caused by it, okay, is 15 newtons. The acceleration of the 20 kilogram mass is 1.3 meters per second squared up the ramp. What's the force pulling the 20 kilogram mass up the ramp? Okay. The ramp is frictionless also, by the way. That's written down. Nope. They're in opposite directions. Same vectors. Yep. 41 newtons up the ramp. We said in every Newton's second law problem, you're going to solve for F net, or you're going to use the two ways to solve for it in each question. M times A, or the sum of all forces. Now, I can't start with the sum of all forces in this question. I did in every single other question we've done, but in this one I can't. But I do have mass and acceleration to start this one off. So can I calculate F net that way? I'm going to use both of those. I just don't always do it in the same order. Sometimes I do sum of all forces first, sometimes I do it second. Okay, so first thing I'm going to do is calculate F net. And I'm going to go M times A, because that's what I have right now. Right? So I'm going to go 20 kilograms times 1.3 meters per second squared up the ramp, and that's going to give me 26 newtons up the ramp. That's my net force. That's the sum of the applied force, FA, going up the ramp, and the 15 newtons down the ramp. The vector sum of those two forces. So what we're really saying here is this. F net equals the force applied plus negative 15 newtons. Because the force applied is up, and the force down is down. Well, 15 newtons is down. Okay, so now when I want to solve for F applied, I'm going to subtract negative 15 newtons. So I'm going to have F net minus negative 15 newtons equals FA. So that's positive 26 minus negative 15. That's positive 41, or what we should write, 41 newtons up the ramp. Now, any tough math in that? Not really, okay? But getting to the math, that's trickier, okay? That's what makes Newton's second law stuff challenging, is not the math, okay? I mean, I say all the time, you do not need to be good at math to be good at physics. It doesn't hurt, okay? But it doesn't guarantee it either. I'm a perfect example of that. I'm not a terribly strong mathematics person, okay? But I can do physics, because the math in physics isn't terribly complex, at least at this level, right? As long as I can visualize what's happening in a given situation, I can figure out what math to do. That's the trick, is figuring out what math to do from the context of the question, okay? And the other side of this is also true. Being good at math doesn't guarantee you're good at physics. In fact, I've had several people who were brilliant at math, and they really struggled with physics because they just wanted to do the math. I'm like, now math is a tool, and you got to figure out how to use the math, okay? And that was challenging for them. All right, let's have you try to draw this one. Okay, let's just draw it for now. It's a pretty easy question, but it's also a new type of Newton question. Okay, so I'll give you a minute to get it written and drawn out. Okay, so this type of problem is what we call a system problem. In a system, there's more than one mass. Okay, so in this situation here, there's a 10 kilogram mass that's got the applied force of the rope being directly applied to it. And then there's a 20 kilogram mass that is attached to the 10 kilogram mass by another rope. Okay? Do the 10 kilogram mass and the 20 kilogram mass accelerate at the same rate? Okay, let me ask it a different way. Have you ever seen a like a semi-truck that's got like the one trailer and then it's got another trailer behind it? Do they accelerate at the same rate when the truck pulls away from the light? They better, because if they don't, one of them is going to disconnect or smash into the front one. They don't generally do that, okay? This is no different. If I'm pulling on this rope, those two objects have to accelerate together because they're attached. They're part of a system. All the parts of a system have to have the same acceleration, right? They don't have to necessarily have the same forces acting on them. These two don't. But they're going to accelerate at the same rate because they're part of a system, they're connected, and can do nothing else. Okay? So right now, they tell us that the force here is 55 newtons. And they tell us that the force of friction on the block system is 44.1 newtons. Can I simplify that diagram? How would I do it? Exactly. If they're going to move together and do exactly the same thing, I can represent them as a single mass. When I'm being asked about the whole system, I can do that. Okay? So there would be 55 newtons going to the right and 44.1 newtons acting to the left. Okay. Can I calculate the net force on the two blocks? Okay, so F net, still the vector sum of all forces, so 55 minus 44.1, okay, should give me 10.9 newtons, right? And then they want the acceleration of the blocks, plural. Since they're going together, I would take the net force and divide by the mass of the blocks, plural. Okay? It's a system. I find the acceleration of the system by dividing by the mass of the system. Okay? So, that should come out to like 0.36, right? Meters per second squared to the right. Okay? Everybody okay with that? All right. So the next step in a question like this is to ask you about forces within the system. All right? Like for example, what's the tension in the rope connecting the two boxes? Okay. When you were a kid, did you ever pull a wagon behind you? Maybe you still do, I don't know. Okay, but when you pull on a wagon, can you feel the wagon pull back on you? Right? You feel that, right? You try and go forward and it feels like you're being resisted. Okay, well, that's similar to this. The 10 kilogram block is pulling forward on the 20 kilogram block, and the 20 kilogram block is pulling backwards on the 10 kilogram block. That produces a tension in the thing connecting the two of them. So, I should be able to then break a system down into its parts and calculate forces that act within the system, provided I know enough of the forces. Okay? Everyone all right with that? Okay. The key thing to remember is, I just figured out the acceleration of the system as a whole, which is also the acceleration of all of its parts. This number applies to both, together or singularly. That is their acceleration. Okay, that's going to be important for what we do next. So, ignore number one for right now. Now we're doing question number 2. Okay, so now they're giving you an additional piece of information. All the stuff we just did is still true. The acceleration here is still 0.36 meters per second squared to the right. The total friction, okay, is still 44.1 newtons. Okay, that's in total on the entire system. Okay, we'll just write total beside that. The additional piece of information they give you is that the force of friction on the first block is 14.7 newtons. Okay? They want you to find the tension in the middle rope. There are two ways to do this. You can choose whichever block you want. There's a way to calculate that force using either one of the blocks. Okay? I'll give you a few minutes to think about that one. Whatever block you choose, draw the free body diagram for that block. Okay, in case you're stuck. How big is that force? 55 newtons. That's the force that's pulling forwards, and it's directly attached to the 10 kilogram mass. Okay? The question tells us that the force pulling is 55 kilograms. How many forces are acting backwards on that mass? 2. The force we're looking for, the tension in the rope, and the force of friction. If you were thinking of using the 20 kilogram mass, the free body diagram looks a little different. There's the force we're looking for. There's the force of friction. The only thing that's different with the 20 is you don't know this number yet. You can calculate it, but you're not given it directly. Okay, see if that helps anyone kind of get going there. All right, so if I'm using the 10 kilogram mass, I know the acceleration of the 10 kilogram mass is still 0.36 meters per second squared to the right. So what can I find since I know that the mass is 10 kilograms and the acceleration is 0.36? Net force, right? I can just go mass times acceleration. So if I'm using the 10 kilogram mass, I'm going to go F net is m times a, and I'm going to get that the net force is 3.6 newtons to the right. Okay, everyone all right with that? Now, since F net is also the sum of all forces, I know this 3.6 newtons to the right is 55 plus the force of friction plus the force tension. And I also know the force of friction. Here's the trick though. It's negative because it's backwards. It's in the opposite direction of the 3.6, right? The 3.6 and the 55 are both to the right. The 14.7 is to the left. It's resisting. So if I want to find this force, can I subtract these two forces over to this side? Okay, so I'm going to have 3.6 minus negative 14.7 minus 55. When I do that, I should get 37 to 2 significant digits. Right? I think so. To 2 significant digits. Okay? 37 newtons left. If you do that on your calculator, it comes out negative, right? So if I put that in, I'll have the 3.6 minus negative 14.7 minus 55. Right? Comes out negative. That makes sense. The force of friction is holding the 10 kilogram mass back. It's pulling backwards on it. Okay, and there would be my final answer. Again, did I have to do any really complex math? I had to add and subtract and multiply. And that's it. Okay? But it's the context. I have to see what's happening in order to get there. Now, we said you could also solve this with the 20 kilogram mass. But here's what you had to do. The force of friction on the 20 kilogram mass is the total amount of friction minus the force of friction that was acting on the first mass. Okay, so if you did that, you could get the force of friction on the 20 kilogram mass, so 44.1 minus 14.7. Okay, so on the 20 kilogram mass, that's the force of friction. Okay, so there's your force of friction, okay, and that's the force tension. Should I get the same number doing it this way? right? If I calculate the force tension, it should be the same number, right? It's gonna be the same direction. From the 20 kilogram mass's perspective, the rope is pulling it forwards. From the 10 kilogram mass's perspective, the rope is pulling backwards. Okay, so first thing I want to do, calculate the net force. Okay, the net force on the 20 kilogram mass is mass times acceleration, 0.36. Okay, so I get 7.2 newtons to the right. Okay, that's the net force acting on the 20 kilogram mass. Okay, I also know that F net equals the force of tension plus the force of friction, which is negative because it's backwards. Okay, and then if I want to find force of tension, I take my net force, 7.2 minus negative 29.4, and I get 36.7, but it still comes out to 37 newtons. Right. And still get the same number. Doesn't matter which box I use, that rope is pulling on them in the same way. Not the same way in terms of direction, but in the same way. Okay? It is pulling with 37 newtons worth of force. All right. Everybody okay with that? Okay. So a question like that, again, not mathematically challenging, but you got to think about it. Okay? You really got to visualize and go, okay, here's this box. What's happening to this box? Well, friction is slowing it down this way and it's being pulled forward by this. How do I diagram that and go from there? That's the really tricky part. Okay, I'd like you to try question number 1. It's like question number 2. Okay, it's 2 pails and nails or buckets and nails, okay, but it's vertical. So it's a system, but it's vertical. So it's also an elevator. It's not a lot different in terms of reasoning from number 2. Okay, I'll give you a few minutes on number 1 there. Okay. Anyone want more time on that one? Oh, I left it running again. Okay. Anybody want more time on that one? Okay, so in number 1, we've got the 2 buckets of nails, right? And they're both 5 kilograms. And they're attached by this rope. Okay. We know that the tension in the rope that connects the buckets is 60 newtons. So that's 60 newtons down for the top bucket and 60 newtons up for the bottom bucket. Agreed? Do I know how much force is pulling up on the top bucket? Okay. But the acceleration of the buckets is the same. Agreed? All right. If the acceleration is the same, I only need to calculate it for one of them. And I can't do that for the top bucket. But I can for the bottom bucket. What other force is acting on the bottom bucket?
The force of gravity.
The force of gravity. Okay, force of gravity is mass times the acceleration due to gravity. So 5 times 9.81, which is 49.05 newtons. Okay, so can I calculate the net force on the bottom bucket? Okay, so I've got the net force acting on the bottom bucket. Okay, since the top and bottom buckets are part of a system, they have the same acceleration. And now I can calculate the acceleration of the bottom bucket, which is then also the acceleration of the top bucket, or the whole system. Okay, either one. Okay, so 2.2 meters per second squared. Up. Okay. Again, did I have to do any super hard math? Okay. Didn't have to use like the quadratic formula or anything like that. Right? I just had to go, okay, what do I have? I have this force and I have this situation. As long as I understand that in a system, all the parts of the system accelerate at the same rate, I know that if I can find any part of that system, I can apply it to the rest. Okay? So there's that understanding piece that's necessary in order to get to the math and then solve the problem. Okay. Questions on how that one works? Okay. Okay, copy that one down. Give it a try. It's still a system, 2 masses. All right, they're just hung over a vertical pulley. Okay, how many forces are acting in this problem? If I put 2 masses over a pulley and they're not the same mass, what's going to happen? One's going to go up and the other's going to fall, right? Okay? They're going to go together. They're going to accelerate at the same rate. Because they're connected, they can do nothing else. Okay? One will fall, one will go up. They'll accelerate at the same rate. Okay? So how many forces are acting in the system then? 2. The weight of each one of those blocks. That is the force of gravity on each one. I've got the force of gravity acting on each one of these. So 35 times 9.81, okay, to get that other side. So 35 times 9.81 gives me 343.35 newtons. That's the force of gravity on that mass. And the force of gravity on this mass, same thing, still m times g is 245.25. newtons. Okay? Those are the two forces causing this system to accelerate. One part of it to fall, one part of it to go up. Okay? Can I simplify this diagram now? When I had the 10 kilogram block and the 20 kilogram block, I simplified it by drawing one block. Okay? I can do that here. I'm talking about the system. It wants to know the acceleration of the system. So I treat it like one mass. A 60 kilogram mass, the mass of the system, being pulled one direction by 343.35 newtons and resisted in the other direction by 245.25 newtons. Okay, those are the only two forces, so naturally I would want to calculate the vector sum of those two forces. Would you agree? Okay, so I just subtract the two, right? No, 98.1, sorry, 98.1 newtons, right? Yeah. Okay, 98.1 newtons is my net force. Can I calculate the acceleration of the system? What do I divide 98.1 by? By 60, right? Okay, so the acceleration of this system is 1.6 meters per second squared. That's my final answer. What does it seem like it's missing? Right, it is missing a direction because I can't put one on it. That's the acceleration of the system. I can only give the magnitude. The parts of the system go in different directions. So when it asks, describe the motion of each one of the objects, okay, I can say the 25 kilogram mass moves at an acceleration of 1.6 meters per second squared up. Okay, and I can say that the 35 kilogram mass experiences an acceleration of 1.6 meters per second squared down. But if they ask me what's the acceleration of the system, I can only give a magnitude. Because in this case, the parts go in different directions. Okay, for the 10 kilogram block and the 20 kilogram block, I could say to the right, because they both move the same way. But in this case, I can't. Okay? Everybody all right with that? Okay. Let's see how we do with this one. Still a system question, okay? Still similar to the pulley that we did in the last one, except now you have how many masses? 3. You got the pail, the tire, and the pail. All right, give you a few minutes on that. How many forces are acting in this system? 2. There's no friction. It clearly says that it is a horizontal frictionless table. Okay, horizontal frictionless. So there's nothing acting along the table or the pulleys. It says they're frictionless as well, which means the only forces acting are the weights of the two pails. Okay, this one here, okay, force of gravity, m times g is going to be 58.86 newtons. And this one here, force of gravity, is going to be 78.48 newtons. Okay, 8 times 9.81 and 6 times 9.81. Everyone okay with that? All right, can I simplify that diagram now? I can. All right, now I am looking at a 60 kilogram system. A 34 kilogram system. Sorry, thinking of the last question. 34 kilogram system being pulled one direction by 58.86 newtons and pulled in the other direction by 78.48 newtons. Can I calculate the net force? Hey, just subtract those two or add them, make one negative. Okay, so F net is going to be 78.48 minus 58.86, which is 19.62 newtons. Okay, how do I calculate the acceleration of the system? Does this formula still work? What mass do I use? What's the mass of the system? 6 or 34, right? I got to use the 34 here. The mass of the system is 34 kilograms. So, okay, I'm going to get 19.62 divided by 34 kilograms. Now I'm going to get my acceleration, okay? Because it's accelerating the whole thing. But notice it says magnitude, because the tire is going to the left, the 8 kilogram mass is falling, and the 6 kilogram mass is rising. They're all going different directions. So all I can do when it asks for the system's acceleration is, in fact, give the magnitude. Okay, that's it. 0.5, pretty sure it's 0.57, right? Okay. Meters per second squared, and that's all I can get. If it asked for the tire, I could say 0.57 meters per second squared left. Okay. If it asked for the 8 kilogram pail, I could say down. But it didn't, it asked for the system. Okay? All right, on Friday of this week, your quiz will have simple Newton problems. This would be not on the test. Systems, okay, not on the test. I don't think I put a system on there. If I did, it would be a super, super simple one, okay? So it's all collinear forces, okay? Like the problems, like the elevator problems and things like that. That would be like the trickiest stuff that would be on there, okay? I think it's quizzes 0 through 3, okay? And the practice quizzes, that'll be helpful for this Friday's quiz. All right, we're gonna work on more complex Newton stuff tomorrow.